Okay, section 14.7, interference of sound waves. Sound waves can interfere, they can interfere with each other. Take a look at the device shown in the figure. Sound from a loudspeaker at S is sent into a tube at P, where there is a T-shaped junction. The sound splits and follows two separate pathways, which are indicated by the red arrows. Half of the sound waves travel upward, half downward. Finally, the two sounds merge at an opening where a listener places her ear. If the two paths R1 and R2 have the same length, waves that enter the junction will separate into two halves, traveling the two paths and then combine again at the ear, producing constructive interference, and the listener hears a loud sound. If we adjust the upper path so that it is one full wavelength longer than the lower path, we again get constructive interference. From this, we can conclude that if the path difference is zero, or some integer multiple of wavelengths, then constructive interference occurs. This can be depicted mathematically as shown. Now, let's imagine adjusting one of the path lengths R2 so that the upper path is half a wavelength longer than the lower path R sub 1. In this case, an entering sound a sound wave splits and travels the two paths as before, but now the wave along the upper path must travel a distance equivalent to half a wavelength farther than the wave traveling along the lower path. As a result, the crest of one wave meets the trough of the other when they merge at the receiver, causing the two waves to cancel each other. The phenomena is called totally destructive interference, and no sound is detected at the receiver. In general, if the path distance is 1/2, 1.5, 2.5, and so on, wavelengths, if it's these wavelengths, then destructive interference occurs. Oops, too far. You may have noticed that the wires between a stereo system and speakers are usually color-coded, and that the speakers have positive and negative signs on the connections. The reason for this is that the speakers need to be connected with the same polarity. If they aren't, then the same electrical signal fed to both speakers will result in one speaker cone moving outward at the same time the other speaker cone is moving inward. In this case, the sound leaving the two speakers will be 180 degrees out of phase with each other. If you are sitting midway between the speakers, the sounds from both speakers travel the same distance and preserve the phase difference they had when they left. In an ideal situation, for a 180 degree phase difference, you would get complete destructive interference and no sound. In reality, the cancellation is not complete and is much more significant for bass notes, which have a longer wavelength, than for shorter wavelengths, the treble notes. The next section is section 14.8, standing waves.